Hey everyone, welcome to The Explainer. Today, we are exploring the absolute mind-bending world of quantum computing and, more importantly, figuring out exactly what it means for us as we look toward 2026 and beyond. To kick things off, just think about this for a second. A complex calculation that would take our absolute most powerful classical supercomputer literally 10,000 years to solve could, theoretically, be knocked out by a quantum computer in mere seconds. No joke. If you've been following tech lately, you know there's a massive shift happening right under our feet. We're finally moving out of the realm of theoretical physics and stepping right into practical, world-changing applications. All right, here's our roadmap for today. First, bits versus qubits. Second, the magic of superposition. Third, understanding quantum entanglement. Fourth, hardware and quantum noise. And fifth, real-world applications in 2026. Let's jump right in.
Section 1. Bits versus qubits, the paradigm shift. To really grasp the future here, we first need to look at the hard physical limits of the classical computing sitting on your desk right now.
So, the laptop or phone you're using right now, it runs on classical bits. It represents information as a rigid binary, just a 0 or a 1, processed sequentially right through its transistors. But a quantum computer, it uses a quantum processing unit, or a QPU, which runs entirely on qubits. Instead of being locked into a single boring state, a qubit explores a fluid universe of multiple possibilities all at once. Think of it kind of like a giant maze. A classical computer tries to solve a maze by running down every single path one by one. It hits a dead end, backs up, tries the next one. A quantum computer, though, it essentially floods the entire maze with water, exploring every single path at the exact same time to find the exit instantly. It's a complete paradigm shift from sequential logic to parallel possibilities.
Section 2. The magic of superposition, zooming into the microscopic. Let's move on and look at how this builds into the brilliantly weird rules of quantum mechanics that make all this possible.
Superposition is honestly one of the strangest concepts in all of physics. While a classical computer sees a coin as sitting flat, either heads or tails, a quantum computer essentially sees a spinning coin. It's a blur of both heads and tails simultaneously, right up until the moment it finally lands and gets measured. That sheer weirdness, a particle literally existing in a weighted combination of multiple states at once, is exactly how a single qubit can encode and calculate exponentially more data than a standard bit ever could. But how does this actually flow inside a real machine? Well, we don't just leave things spinning chaotically. Quantum computation follows a highly controlled, very precise sequence. Step 1 is initialization, basically setting the stage and resetting all our qubits to a nice, clean baseline. Step 2 is superposition, where we use quantum gates to launch those qubits into that spinning multi-state blur. Step 3 is entanglement, where we mathematically link those qubits together. Step 4 is interference, which acts like a filter for the math. And finally, step 5 is measurement. That's where we force the whole spinning quantum system to stop and collapse into a usable, classical 0 or 1 that we can actually read. Section 3, understanding quantum entanglement, spooky action at a distance. Let's double-click on step 3 of that process, because it brings us to a concept so bizarre that Albert Einstein famously called it spooky action at a distance. When qubits become entangled, they are no longer independent little actors. They become so strongly intertwined that the state of one instantly affects the other, completely regardless of the physical distance between them. Just imagine having a pair of magic dice. If you roll a 6 on one die in Tokyo, the other die in New York will instantly show a 6, without any wires or radio signals connecting them whatsoever. In a quantum processor, this invisible bridge is exactly what allows the system to process incredibly complex correlated information collectively, rather than just one isolated piece at a time. We can actually trace this mathematically with the foundational Einstein-Podolsky-Rosen, or EPR, paradox. An EPR source generates a maximally entangled pair of particles, and one part is sent over to Alice's encoder. Actually, fun fact for you. In physics and cryptography, scientists almost always use the imaginary characters Alice and Bob to represent point A and point B. So Alice gets one particle, and because of that entanglement, its quantum state is forever linked to its distant partner. This exact principle is what opens the door for crazy advanced protocols like quantum teleportation and dense coding, transferring information in ways that classical networks simply cannot do. But wait, how do we actually pull the right answer out of that massive quantum blur? That's where interference steps in. Because quantum states act like waves, they can constructively build on each other or destructively cancel each other out. You can think of it exactly like your noise-canceling headphones. Those headphones listen to the background noise on an airplane and create a destructive sound wave that mathematically cancels it out, right? Quantum algorithms do the exact same thing. They use destructive interference to cancel out all the wrong mathematical possibilities, and constructive interference to amplify the correct answer. It's a massive filter ensuring we actually get a useful result when the music stops.
Section 4. Hardware and quantum noise. Building the machine. Now, capturing all that microscopic weirdness and forcing it to do math inside a physical machine is, frankly, incredibly difficult. The big tech giants, we're talking IBM, Google, the heavy hitters, are currently battling it out using 3 completely different physical architectures. First, we have superconducting qubits. These rely on circuits inside massive dilution refrigerators, and to stop the atoms from jittering, they have to be cooled to near absolute zero. That is literally colder than the vacuum of deep space. Then you have trapped ion qubits, which use electromagnetic fields to trap charged atoms and poke at them with lasers. And finally, photonic qubits. These use actual particles of light and have the massive advantage of being able to operate at room temperature. But listen, no matter which hardware you're rooting for, they all share one fatal enemy: decoherence. Qubits are unbelievably fragile. It's kind of like building a massive 10-story house of cards while sitting in a drafty room. Even the absolute slightest breeze is going to bring the whole thing crashing down. For a quantum computer, that breeze could be a microscopic temperature fluctuation, a stray electromagnetic wave, or even just a minor vibration. When decoherence happens, the superposition is completely destroyed. Errors multiply, and your calculation is completely ruined. So let's ground the hype in some reality for a second. We are currently in what researchers call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Right now, error rates are still pretty high, and fully fault-tolerant systems are still sitting in the development phase. But we definitely aren't at a standstill. Early commercial pilots and hybrid systems are already out there running, proving their immense worth on some highly specific, highly complex problems. Which naturally leads to the big question. With all this incredible parallel processing power coming over the horizon, will you be tossing your traditional computer in the trash? Are we going to be buying quantum smartphones anytime soon? The simple answer is no. Quantum computers are absolutely not meant to replace classical computers. The future of computing is 100% hybrid. I mean, you wouldn't use a Formula One race car to go pick up groceries, right? In the exact same way, classical computers are your trusty daily driver. They are actually way better at handling everyday workloads, sending emails, managing databases, loading up web pages. What's going to happen is that your classical computer will just seamlessly outsource the heavy lifting, like massively complex molecular simulations, to quantum supercomputers living out in the cloud. Section 5, Real-World Applications in 2026. Why it matters. Let's see exactly how this hybrid future is going to reshape our everyday lives as we look to 2026 and beyond. Being able to simulate molecular behavior natively is an absolute game changer across so many industries, and the human impact is going to be staggering. Traditionally, pharmaceutical drug discovery takes 10 to 15 years and costs billions of dollars. But quantum computers, they can model protein folding with unprecedented accuracy, potentially slashing those timelines and helping us cure diseases that have stumped us for decades. In climate modeling, we can optimize global renewable energy grids to actually help tackle the climate crisis. Over in material science, researchers are already using quantum simulations to design fundamentally better EV batteries and carbon capture tech, completely skipping the need to test thousands of chemical combinations in a physical lab first. It is breathtaking stuff. But of course, it's not all perfectly rosy. There is a massive security storm brewing. Back in 1994, Peter Shor proved that a sufficiently powerful, fault-tolerant quantum computer could efficiently factor large numbers. What does that mean for us? It means it could theoretically break the RSA and ECC encryption systems that currently secure basically everything: our online banking, our VPNs, our private digital communications. You can think of Shor's algorithm as a ticking clock for cybersecurity, a sort of quantum Y2K. It's a massive threat, and banks, governments, and major institutions are racing to prepare for it right now, long before the hardware even fully matures.
So as we stand right on the absolute edge of this monumental technological shift, a shift from the rigid sequential logic of ones and zeros to the dynamic, entangled possibilities of quantum mechanics, I want to leave you with a thought. How is your industry going to adapt to the coming quantum disruption? Are you ready for the leap? Thanks so much for hanging out with me on this explainer, and keep questioning the future.